So I'm going to go through them. What I would recommend, okay, it's up to you how you do it exactly, but I'd recommend have the formula down. If you need to put what unit the things are in, maybe put that in parentheses below them. Leave a space so that you could put a sample problem. Does that make sense? Leave a space so you're like, hey, I got the formula. What would it actually look like being used? Okay, for each of these. So without further ado, speed is already up there. I left one. This is I think it was the first formula I taught you when I got here. Distance divided by time. On this formula, it could be any units. Okay, so distance could be anything from inches to miles to kilometers, whatever. All right. And time could be seconds, hours, minutes, days, months, years, whatever you need. Okay? So like if you're talking about the movement of glaciers, you might be talking centimeters or inches per year, right? And that would be your speed. Okay? Any questions on that? Pretty easy. Make sure you're able to use it like backwards. So if you're given distance and time, obviously that's easy. But what if you're given speed and distance? Can you get time? Right? So make sure you're able to use the formula forward and backward. Next one, acceleration. Maybe leave a little space again. I'm not going to leave a space on the board, okay? Or not much of one. Acceleration is A equal to, hopefully you're like, oh, I remember that. I'm going to keep plowing through. Vf minus Vi divided by t for time. V is velocity. We did do a couple sample problems out of the workbook, if you remember, that had an S instead of a V, because they were just dealing with speed. You remember that? So final speed minus initial speed. This is just taking into account, hey, velocity is speed and direction of travel. I'm not going to include any of those direction of travel problems on the test because we barely talked about it. So if you see V or S, F or SI, it's the same thing. Okay. All right, next one. Momentum. Anybody remember this one? For whatever reason, we use a undercase P for momentum, and it's equal to mass times velocity. Okay. Easy enough. Force, we use this a bunch. This will get the most attention on the test too. F is equal to MA. Who remembers what F is measured in? What the unit is for force? Newtons. I only heard one whisper and it came from over this way. So force in newtons, which would be a capital N, right, is equal to mass, which is in what unit? Kilograms, times acceleration, which is in what unit? Meters per second squared. Or meter per second, right? So if you're given a force in newtons and you're given acceleration in meters per second squared in a question, and it's asking for kilograms, you're just going to divide out to isolate the variable, right? Like we did a few times. Work. Work in what units? Joules. You guys are, I'm not blowing smoke, okay? You guys are remembering these better than the other classes. That's good. So work in joules, capital J if you want to abbreviate, is equal to, does anybody remember?
The input
So what goes into work? You have something that we're moving.
Oh, okay. So
The something has a mass in kilograms, right? Times how far, distance, and we measure that in meters. Okay, that's work. Moving a certain mass, a certain distance. Next one, power. Capital P for power, but it's measured in what unit? Think electricity. The English dude. James Watt.
Oh, I knew that.
Watts. Watts. W for watts. Which gets confusing because we have W for work and then we have W as an abbreviation for watts, which is for power. Anyway, power is equal to what? Remember, you could have the same person or two people doing the same amount of work, right? Lifting the same mass or moving the same mass, the same amount of distance. But what makes it more powerful? The speed that they do it in. Very good. So we have a time component dividing the work. Okay? The work in joules. Time would be in seconds. So work in joules divided by time in seconds gives you power in watts. Then we have mechanical advantage and efficiency, which are kind of similar looking. We'll just say MA is equal to, mechanical advantage is equal to, we have force out. Force in what unit? Newtons, right? Divided by force in. So in other words, you have a certain amount of force that you, in the denominator, are applying to the machine, and then you have the machine like turning that force, just direction or intensity over, doing the thing, doing the simple machine thing, applying the force out to the object that you're trying to move somehow, some way. So force out divided by force in is mechanical advantage. Because you're dividing newtons by newtons, those go away, right? So what are your units going to be in for mechanical advantage? You're just going to say the mechanical advantage is 2 or 10 or 1/5 perhaps. Remember, depending on, like the example of the wheel and axle, depending on which side you apply the force to, the axle or the wheel, determines whether the advantage is going to be a number greater than 1, or less than 1. Okay? And then we have efficiency. EFF. They show it lowercase. I don't know if that matters. Why not? And that is equal to, this is why it looks familiar, because it's work out divided by work in. Times, and I always forget to put times, 100%. You got to convert the decimal you get here to a percentage. I'm going to give you just a second, and I'm going to explain something on efficiency. Everybody caught up? So efficiency isn't going to have a unit, it's just going to be represented by a percentage efficiency, and it will never, in reality, be 100%. Why not? Because of friction. You're never going to have, in reality, there never has been, if you did get one, get a Nobel Prize or something. Because of friction, there's never a perfectly efficient machine. You're going to have some kind of loss of energy, okay? Also, you will never have more than 100%. if your answer, remember how after you answer something, you should be like, does it make sense? Does my answer make sense? Does it pass the sniff test? For this one, the most common mistake I see is you flip your work in or out, okay, in the division problem, and you end up with more than 100%. That's impossible. So it doesn't pass the sniff test. You probably have these flipped. How do I know it's impossible? Because we learned about the law of conservation of energy. You would need to be creating energy. That machine would have to be creating energy in order to have an efficiency greater than 100%. It's just not, you'd be breaking the laws of physics. That one. Okay? Any questions on that? So when you're studying today, this is the way I envisioned. It's worked for a couple of classes. It hasn't worked for others. Basically, if you put in the work, it's going to work for you. What I want for your study guide, so it's all in one place. You'll have all these formulas. I want you to put an example for each one. And once you've done that, I want you to create a worksheet. At least one example of each. So start by just doing an example of each. It could be the one you put here, okay, to give to someone else. Now, hopefully you didn't all use the same one. So if you're making it up, that should make sure that you're not getting the same problems as so that way you can exchange tomorrow when you get to class and say, here, work this worksheet out as practice. Because we haven't done a lot of practice. We've done all these examples along with the workbook stuff, right? But we haven't done much practice. So I wanted to give you that chance. All right? So you've got 8 problems to come up with for your sheet, and then put it on a separate piece of paper too. Just make sure you're not like taking from there's examples in the reading, right, in the workbook. We could just change the numbers on them or something. But make sure they don't violate any laws of physics. Make sure the answers make sense. If you can't answer the question with it making sense, then your partner won't either, okay? So for right now, you're working by yourself, yes?
Mm-hmm.
Okay. Go ahead and get started.